30, so it wasn't
Oh,
bad.
that's really good. That's really, really
Yeah.
good. Fantastic.
And just, yeah,
What
because
you
on
got?
one of the questions it said, what are the uses for glucose? But I wrote amino acids twice by accident. So,
Okay, you lost a point
yeah.
there.
Yeah, and then the other two, sorry, were just, I think they were, I genuinely didn't know this, so I think that was just the problem
Oh,
with those
okay,
two.
okay. What kind of question? What kind of question was it? You remember?
Um, um, I can't remember it, but when I get my biology book back,
Yeah,
then
no problem.
because she's just marking it, and then she has to quarantine it for 3 days, so
Of course,
when I
yes.
get it back, yeah,
Okay, no problem. Okay. So yeah, just to remind us what we learned about then, we learned about momentum, this
yeah,
P, which is just the product of the mass times the velocity. Yeah.
yeah, okay,
I'm just read off the key points here. Okay. And the key
yeah,
thing is that a closed system is a system in which the total momentum before an event is the same as the total momentum after the event. So what we say is
yeah,
that momentum is conserved. Now I've got a little simulation here, which I am going to bring up. Oh, is it already up? No. Do I stop that? Okay, there we go. Now I'm just going to share this screen with you.
okay,
How do I share? Yeah, you share. Okay, so here we've got two trolleys. I
yeah,
can select the mass, okay, make them each 1 kilogram. All right. Um,
yeah,
and these are the velocities. Now, the -5 here, Jay, what this simply means is that it's going in the opposite direction to the 5. So they've selected here a convention, which should always do when you're doing sort of vector problems. You should define which direction is your positive and which
yeah,
direction.
yeah,
So anything traveling to the right, in this case, is being treated as having a positive velocity. Anything to the left
okay,
as a minus velocity. Okay.
yeah,
So
okay,
the initial velocities they're all going to have are going to be 5, and this one is -5 as its initial velocity. Now, if
yeah.
they start off on their journey, firstly, what's your prediction? If they get stuck
Um,
together, what do you think will happen? Let's assume that there's some sticky tape.
well, they're traveling at the same velocity towards each other, same mass,
Yeah.
so aren't they going to have the same momentum? Um,
Okay, so momentum is a vector. Yeah.
yeah,
So
yeah.
one is going
Oh,
that way and another one is going that way. The
oh,
direction
so
is different.
is the red one going to have a momentum of 0. No, as 5 going
Yeah.
towards the
One
right, and
kilogram
then
times that one. So it's going to be positive 5 kilograms
yeah,
per second. And the blue
yeah,
one is going to have -5
yeah.
kilogram meters per second. So what do you reckon will happen when the 5 and the -5 meet? Do you reckon one's
Um,
the other one way, or are they going to stop? What do you reckon will happen?
will they just stop because they're both traveling at the same momentum? They're both going to have the same momentum, and they
Yeah, and you're absolutely
yeah.
right. Okay, so it gets to 0. What about if I use the slightly, let me reset this. If I use a slightly heavier mass?
Then will the blue one, be going um have a higher momentum, so it's going to maybe
Yeah,
push the red one backwards.
yeah, and there we go. And
Yeah,
you can see the red one now has -1.7, whereas the one going this side is 1.7. Okay, right.
yeah,
Okay, so we might come back to this demo. Now, obviously here, what we're seeing here is that there's something known as an elastic collision and an inelastic collision. So normally, if you're looking at, say, when people are playing snooker or playing pool, what you see is that the collisions, when you hit one ball with the other, they don't
yeah,
normally stick together, right? So that is
yeah.
what we call an elastic collision. So in an elastic collision, kinetic energy is also conserved. Now, if I try the same demonstration, and this was an elastic collision, right?
Yeah.
There's now springs, if you like, as buffers. If I do the same,
Okay.
even though this has a momentum of 5 kilogram meters per second, and this has a momentum of -5 kilogram meters per second, if I try the same thing now, Yeah, oh, I meant to do it with 1 kilogram. Sorry, I should have used the same mass. If I can do
Okay.
the same thing,
Oh, they go back because it's an elastic spring, so they're going to be going back at the same momentum as well.
absolutely. All right. So it's like
Hmm.
there's a swap there. So it's a bit like what happens when you notice that Newton's cradle. So in Newton's cradle, the collision
Yeah,
between those spheres, we call them, or they're known as elastic collisions. So in this one, the
yeah,
thing is kinetic energy is conserved. Now, of course, I can try it with a slightly bigger mass as well, so on and so
mhm,
forth. Yeah, which we might look at some stage later. So
yeah.
I'll bring you back to this board just to discuss phenomenon almost as it were. So if I have two trolleys, let's imagine that I have not a spring as such, but an elastic band.
Okay.
All right. And I stretch it so that it's really tight. So in other words, there is elastic potential energy in this. Yeah.
Yeah,
And let's imagine that this trolley here has been loaded with extra weights. And for
okay.
argument's sake, we're going to say that it is at 10 kilograms. And this trolley here is at 2 kilograms.
Yeah, yeah,
So I'm keeping them apart with my hand because I've stretched this piece of elastic. Okay. Now, when I
yeah.
let go,
Mhm.
what do you think will happen?
Will it, so the 10 kilogram ones are going to move faster into is it going to push, no, no, they're on elastic.
So they're
Is it
on
going
an
to,
elastic, so it's stretched. So obviously it's going to want to pull them in, isn't it?
yeah, so is
Let's
it
take
going to push,
so there's on this 10 kilogram, there's going to be a
yeah,
force acting that way, and on this guy as well, there's also a force acting that way.
yeah, yeah.
Yeah, because it's a stretched elastic band.
But
Yeah.
isn't the 10 kg force greater than the 2 kg? The one on the left is greater.
Well, they're in the same piece of rope or same piece of
Yeah.
plastic,
Uh-huh.
the same piece of elastic. It can't have two different forces,
Oh.
parts of it. It's not possible.
Oh, okay,
Yeah.
okay.
Otherwise, if it did have, then there would be a resultant force on the elastic band itself, and then it means that the elastic should be moving in a certain direction.
Okay.
Actually, this is probably not as intuitive, but here the forces are the same. The force that this feels is the same, exactly the same as the force that that feels.
Okay, yeah. Yeah.
Okay, so now we know that the forces are the same. So we can even think about it and relate that formula. Can you remember that formula that relates force, mass, and acceleration?
Um,
Resultant force, shall I say more specifically?
um,
So resultant force is equal to, sorry if you can't remember it,
yeah.
mass times acceleration. Okay, so if you know the
Yeah.
mass, you know the acceleration, you can work out the resultant force acting
Yeah.
object. Okay,
Okay.
cool. So if I tell you now that this is the force and that's the formula, which of these is going to have a greater acceleration?
Is it gonna be the 10 kg one? It's gonna have a greater acceleration, but no, hang on, it's not. Are they gonna have the same? Because yeah, like I said, the elastic
Well, the
is,
force is the same in the two
yeah,
elastics, on both sides of the elastic band, if you like. The
yeah,
force
yeah,
that this 2 kilogram is feeling is the same. Now, obviously, I haven't put values. You can put values if we want.
yeah.
We can call them 10 newtons each. So which one will
Uh-huh.
have a greater acceleration?
Oh, will it be the 10 kg one because the mass is just higher?
Okay, so if you use your formula, if that's 10 and the mass is 10 kilograms,
Yeah.
what acceleration will that 10 kilogram object have? Again, if the result
Uh,
is 10, and this time the mass is 2 kilograms, what acceleration will the 2 kilogram mass have?
will it be the one with the 2 kg have a higher acceleration because you're dividing by a smaller number?
Absolutely. So this will therefore have, if you like, an acceleration of 5 meters per second square. This
Yeah.
here will only have an acceleration of 1 meter per second square. And if you
Uh,
do the demonstration, if you try it in school,
yeah.
you'll notice always that the smaller mass travels much, much further. So when you
Uh-huh.
let go, these are not going to meet in the middle.
Yeah. Okay.
Yes, they're going to meet more towards the end of this 10 kilogram. It would have traveled a far shorter distance.
Yeah. Okay.
Okay. And because
Yeah.
also it's because its acceleration is far less than the acceleration of the 2 kilogram mass, which is essentially changing its speed by 5 meters per second every second here, whereas this is only changing its speed by 1 meter per second every second.
Okay. Yeah.
Yeah, okay, you're happy with that. All right.
Yeah. Yeah.
So this is a good demonstration for momentum as well. So what we're looking at here is we're seeing two equal forces, all right, on each one, but it's also it's a demonstration or one that you look at when also coming up with this relationship of force equals mass times acceleration. So
Yeah.
let's try and look at and we looked at Newton's third law. It's probably a while if you remember about me pushing a wall and about the fact that forces always act in pairs.
Yeah.
Yeah, us having that discussion.
Oh yeah. Yeah.
Good. All right. So let's have a go at. So we've got number 2.
Two. Okay.
Yeah, I'll just switch my screen so you can see. Rusty.
Yeah. Yeah.
There we go.
Okay. Wait, did you say number two? Sorry.
Yeah, number 2. Yeah, correct.
Okay. Yeah. Just
2
checking.
A,
Yeah.
B, and C.
Yeah. Okay.
Cool.
And is the units meters per second squared?
For
Like the
momentum,
yeah. Yeah.
no, it's because it's mass, which is kilograms, and
Okay.
velocity, which is meters per second. So when you times the two, you get kilogram meters per second. Okay,
Okay.
all right.
Uh,
Feel free to use the information in the key points as well here.
yeah. Okay.
Okay, no
Thanks.
problem.
So for A, I got 400 kilograms meters per second,
Well done.
and then for B, I got 0.5 meters per second,
Yeah, absolutely.
and then for C, I got 100 meters per second.
Then you got 100 meters per second for that one. Okay, well done. Okay, so let's try and move on to number 3 then. Let's see if we can tackle number 3 slightly more challenging. So the key thing here, Jay, is it says describe, which means they're not asking you to make any calculation,
Yeah.
purely
Okay.
description, okay?
Okay. Do you want me to say it or write it to
Yeah,
you?
just say it to me, that's fine.
Okay. So when they push each other, the 60 gram person will. No, won't the forces be the same actually? The
They
forces are
are, exactly. That is what they want to see, if you understand. So they'll be
yeah.
pushing each other with equal but opposite forces.
Yeah,
Okay?
it's just that the 60 kg person will move back at a faster acceleration.
They'll move back at a fast acceleration. You're absolutely correct. Or even at a faster speed. You're right. Yes, good.
Yeah.
Then it says the momentum each skater has just after they separate.
Okay.
So now remember, momentum is a vector.
Yeah, yeah.
Okay? So it's got direction. So how can you describe the momentum that each skater will have?
Well, won't the momentum of the 60 kg person be greater than the 80 kg person?
Yeah, it almost makes you want to think that, isn't it? But
Mm.
actually, no. The
Uh,
momentum will be the same in terms of size, and the
yeah.
direction will be in the opposite direction. Okay?
Okay.
Momentum is always the same in such a scenario of the
Mhm.
two. All right. And it's the reason why. So if momentum is the same, mass
Yeah.
and velocity, this 60 kilogram will be multiplying by to a bigger velocity, whereas that 80 will only multiply to a smaller velocity if the two momenta are equal. So in this
Yeah.
case, you would have to say the two momentas are equal in size, in magnitude, but opposite in direction.
Okay.
Okay,
Okay. Yeah.
good. So now it says describe each of their velocities just after they separate.
Okay, so the momentum will be the same, but then the velocities, the 60 kg person will move at a faster velocity than the 80 kg person.
Correct. And also you want to mention they're going to move in opposite
Oh, opposite
direction
directions.
because
Yeah.
it's a vector. Okay. So you want to talk
Yeah.
about direction there as well. Good.
Okay.
Their total momentum just after they separate.
Um, will that differ? Because
Well, it's asked you a question. It says their total momentum. So if this person has got the same sized momentum, but because it's in different directions, let's assume that the one who goes to the left, we're going to give them a negative momentum, and the one who
okay.
goes to the right, we're going to give them a positive momentum. So what did you say
Yeah.
about the sizes, the actual value, the number of the momentum itself? It will be the same. Are you happy?
Yeah. Yeah.
So if I add the two to find the total, what result am I going to get?
Will it be smaller than the for the?
All right, just to make life easy then, let's assume that the total momentum, or the momentum that the lady has, is 480 kilogram meters per second. Yes.
Okay.
So what
Yeah.
speed does she have? What's her velocity? So
So
remember,
four.
yeah, 480 kilogram meters per second.
So would it be 480 times 60?
Not quite. Remember, that's the product. So momentum is equal to
Oh,
mass times velocity. So if she
yeah.
has a momentum of 480 kilogram meters per second, what
Yeah.
velocity would she be moving with?
Okay. So it's
So you're
P
gonna have
divided.
to, yeah, absolutely. You're gonna have to rearrange that. Good.
So 480 divided by 60 is 8. So she'll have a velocity of 8 meters per second.
To the right.
To the
Good.
right, yeah.
What about this person? What velocity will they have?
So they're going to have this 480 again divided by 80,
Yeah.
which is going to equal to 6 meters per second to the left.
Well done. Now,
So, so the person, the woman, she's going to move at a faster velocity to the right.
yeah.
And then momentum wise,
So now let's compare the momentum. Their total momentum. So just after they separate. So just after they separate, this guy is going to be, what would his momentum be? It's 80 times 6 meters per second to the
yeah,
left. What value does that give you?
400.
80 times 6 meters, 480. But because it's momentum, we need to pick a direction. So if it's going to
400.
the left, you might have to call it negative. So we're going to say it's negative 480 kilogram meters per second. Yeah.
Yeah.
Now, what about this person, the lady? What will her momentum be? It'll
Well,
also
hers,
be 480, but it's going to be positive.
yeah, yeah,
It's going the other way.
yeah, yeah.
If I add the two values of momenta, 480 plus minus 480, what do I get?
960 to
Not
the
quite,
left.
not quite, no.
Oh, sorry.
480
Um,
plus minus 480.
oh, will it be 0?
Correct. So the total
Oh,
momentum just after they separate is 0. Because this one has
oh,
a momentum that's going same size, but different sign. One is positive, one is negative, and they're the same magnitude. If I add two numbers of equal magnitude, but different signs, I get 0.
oh, okay. Yeah,
Okay? So just one to remember there. Good, you're doing good. Number
okay.
4 now. Have I got number 4?
4, okay. Is it 120?
Yeah, kilogram meters per second. The other unit you use,
Yeah,
we'll look at it anyway after you've finished this part.
okay.
Okay. What about 4 part B?
Do you mind if I just quickly grab the calculator? 'Cause we're probably going to need
Yeah,
it.
go
So.
for it. Yeah, absolutely. You will be needing it for the rest of the stuff. That's good. No problem. Unbelievable. While you were gone, I just quickly had a glance at the Brighton Man United game, and
Yeah.
Brighton are trailing behind 2-1, but they've hit the
Yeah.
woodwork 4 times.
4 times. Oh my God.
That's
Yeah.
very interesting. You hear it happening 2 times or 3 times, but 4 times.
4 times. Wow. Yeah.
They'll be very, very saddened by that.
He
But at least
didn't
they know
only
that they
go
tried.
1-0 at the start.
Yeah, and then it was
Did Man
1-1, and it's now 2-1.
Oh,
Yeah,
was it? Oh, okay.
yeah, so it's 2-1 at the moment, but there we go.
Yeah.
Luck is not on
Brighton
their
will bring it
side.
back. Yeah.
Yeah,
4 times. Wow.
I know.
So 1.5 is for
It's
B.
1.5 meters per second. Well done.
Yeah.
Okay, good. So you've applied that idea that the momentum of the other person must be equal to the other person. So that's the key thing when you're answering such type questions. Now
Yeah.
we're also going to apply this so-called law of conservation of momentum. What you actually did there was you were applying the law of conservation of momentum when you're working out the velocity of the other skater. So we
Yeah.
say that the momentum before something happens, before an event, is
Yeah.
always the same as the momentum after an event. So normally when you talk about an event in physics, we're talking about either collision or we're talking about an explosion, so to speak. Okay?
Yeah.
All
Mhm.
those are classed as events. So the
Yeah.
key thing to always note when you are bring my board to this, so we can start looking at this new idea. And that is the idea of, it's also known as the law of conservation of momentum. And what that states is that the total momentum before an event is always equal. It's always equal.
Yeah.
Total momentum after the event. Okay?
Okay.
And we're going to be applying this law. Now, you've already applied it, like I said, so you've already got the hang of what's going on here, but we're just going to make it, formalize it a little bit more in its application. So if I had, let's just imagine, car,
Yeah.
and I've got a stationary trailer. So this is before the event, and I'm assuming that my car is traveling with a speed of, say, 30 meters per second, and it's got a mass of 500 kilograms,
Yeah.
and it's an empty trailer, which happens to be 100 kilograms, which is stationary.
Yeah.
They then collide. So this is before the event.
Yeah.
Now, after they collide, in such a manner that the 100 kilogram trailer is now attached to the 500 kilogram car.
Okay.
Now, if I had
Yeah.
to ask you a question and said, what would be their common speed?
Um, their common speed.
Yeah. So their common speed, because they're attached together, aren't they? So they're going to be
Yeah.
moving together. So that's what speed will they be moving together?
Oh,
That's what I mean by their common speed. Because now
so
this is attached to that.
yeah.
Okay.
So what would happen is Or if you work out the momentum
Yeah,
of
so
the car, the truck car,
so we've got to work out the, you're absolutely right. And what we've got to do is we've got to work out the momentum before the event. And we know that this momentum will be equal to the momentum after. So before, when I've got my car, so I've got, if I just write my formula here to say P is mv, yeah. So
yeah,
500 times 30 plus the momentum of that, which is 100 times 0.
yeah,
This must be equal to, I can split these into two and write the momentum for the car. 500 times V, which I don't know, plus 100 times V. That's the
okay,
momentum after.
yeah, okay,
Yeah.
yeah,
Now this can simplify. I'm going to put my equal to sign here. This can simplify, can't it? What would this simplify to? This is 500 times V plus 100 times V.
oh, would it just be 600 times V?
Yeah, correct. So 600 V. And now this here is obviously 0, 0 times 100, 500 times 30. I now get something that says 15,000, right? So now it's
V,
just
yeah.
algebra really to work out V.
Oh, okay, so it's just 15,000 divided by,
Yeah, or 150 divided by 6,
yeah, we should get 25.
25, good. So I get
Oh,
V
so then you know
equals
your velocity, the
absolutely
the same velocity is 25 meters per
correct.
second.
You're absolutely right. So this V will travel off together at 25 meters per second.
Ah, okay,
Okay.
okay,
And that is
yeah,
just purely by applying the conservation of momentum law. Okay.
yeah,
Now, another scenario where you may be asked, so apart from things colliding and then sticking with each other, and that said, actually, let's try and have a look to see, not that one. One moment, there's just one more screenshot for you. Which we're gonna look at. Where is it? Okay, let's try and have a go at this then, Jay.
okay,
Okay, so I'm just trying to see here if I can share both screens. Okay, so you got some questions there, Jay, on the left side of the screen. Hopefully,
okay, yeah,
yeah. So using the first example as the basis, have a go at question 1.
okay. Do you want me to put the visualizer on as well so you can
Yeah,
see
go
it?
for it so I can see what you're doing. That would be great. Thanks, Jay.
So, okay, so, No, wait, hang on, sorry, I don't know. So 5 times 1,000
Okay.
plus.
Even though it's just watch what it's saying, it says calculate the momentum of the wagon. So it's just the wagon at once.
Oh, okay.
So all you need to know for the wagon is what's its mass and what's its velocity. Yeah, so it's 1 mark for that part.
1,000 times by 5
Yeah,
equals to 5,000 kg meters per second.
correct. The other unit you can use for momentum, by the way, which I
Yeah.
was going to tell you, is the Newton second.
Newton said, oh, okay, that'll
Okay,
probably
that's
be easy.
another unit you can use for momentum if you want to save yourself writing too many letters, kg meters per second.
Yeah, but wouldn't that be easier to remember because you literally just times in the kg and the meters per second together anyway?
Absolutely, it's much easier to remember that. You're absolutely right.
Yeah.
Yes, if you decided to write NS, that would also be acceptable.
Okay then.
Good.
Um,
Good. That's the times. Well done.
equals to, and then that's just um and then
So take
is
your time
it
with that one, Jay. So that one is
okay?
very different from this example with the car and the trailer.
Okay.
And watch exactly what I did here. I found the momentum of each of these to get the total before, and I found the momentum of each of these again after they've collided.
Okay, so
Okay?
yeah.
Because they move off together, it says. Collides the stationary. The two wagons move together after the collision. So similar to
Oh,
this, where the car moves together with the trailer.
oh yeah, I remember
Okay?
that. Okay. Oh yeah. And then this is 500. X is equal to 2 meters per second.
Okay, so they move off with a common speed of 2 meters per second. Okay, good. Now,
Yeah.
normally what I advise as well, it's okay to draw a little sketch. Sometimes it just helps visualize. Anytime you've got a momentum problem, just to see that you have not, you've taken into account everything that's presented. Okay,
Okay.
good
Yeah.
stuff. Well done. Number two. Have we got number two now, Jane? It's going to be a lot of working for this one because it's 6 marks. That's at least a grade
Yeah.
7, grade 8 question.
Okay. Okay.
They've given you that, I think, Jay.
Oh yeah, sorry. I've just realised that. Yeah, they've
Yeah,
given us as 0.7,
good.
and then you got to calculate the total mass. But then,
Not quite. So just read the question again. It says, an object is attached to a trolley
okay,
mass.
yeah.
Okay. So an object is attached to the trolley with that given mass.
Oh, so it's just an object on top, or
There's an object on top, correct?
yeah.
So it is
Okay.
that object that they want you to find the mass, the actual mass, to say what is the mass of that object.
Oh, okay. Okay. Yeah.
Yeah.
So it's an object here, and then we're trying to work out the mass of this object.
Yes, correct.
Okay. Oh, okay. Okay. So
That makes sense now?
yeah, yeah,
Good. And that's why a little diagram does help, because now you can see what information you've been presented with.
yeah, and then um. So we know that our momentum of our,
So that is before, that line you've drawn separates the
yeah,
momentum before and the momentum after. So you need
yeah,
to look at all your masses in the before the collision happens, and
yeah,
look what the velocity of each of those masses are, and then you're
yeah.
going to add them together, and that will give you your total momentum at the start. Does that make sense?
Oh, okay, okay. Yeah.
Okay. So each of your objects in there that is moving with a velocity, find its momentum. That's
Ah,
the
okay, I
momentum
get what you
before.
mean. 0.7. Wait, hang on. So be 1 point.
Good. That's a clever way of doing it.
Yeah. Well, you'd come to the same answer even if you doubled this, wouldn't you?
Correct. Absolutely. It's just much quicker. But
Yeah,
remember
okay.
also that you have a mass which is still attached to those trolleys.
Yeah,
So if you draw it
Oh
on,
yeah, the mass is attached. Yeah, still
still
on. Yeah.
attached, still on top. And we
Oh,
don't.
so we, yeah. Yeah. Mm.
Okay? Now, I think it's only on one trolley, by the way, Jay.
Sorry.
That
Oh,
mass is only on one trolley, I think, according to the question.
okay.
It just says that an object is attached to a trolley. So it's just one trolley. Yeah.
Yeah. So we've worked out now the momentum of if that mass wasn't on.
Yeah.
No, actually, no, we haven't. So. But this isn't the actual momentum because we don't know what this mass is. So
Correct. And never be, even if we don't know it, let's just
yeah,
go back to the before the collision.
yeah.
You have some unknown mass M. You know this is 0.8.
Yeah.
That's 0.8. This is before. And this is at 0 meters per second. You know this is traveling at 1.1. Yeah, so you can still, Jay, nothing is still stopping you from forming an equation to say, well, what's the total momentum of everything? This is 0.8 times 0. The trolley here is 0.8 times 1.1. And this mass is mass times 1.1. This is everything I've got at the start before the collision. So this is what I'm going to add all together.
Okay. I get what you mean.
Okay.
Yeah. Mass times 1.1. Yeah. Okay.
Okay, good. So
And
now they
then
collide, and we're going to do the same thing. And then we're going to equate the before and equate it to the after.
yeah. Okay.
Okay, good.
So now that we got this,
Yeah. So we're going to have to make them equal. So what is, if I add the total, well, 0.8 times 0 is just 0. So
yeah,
before, total momentum is what? Is
um,
0.88
0.8
plus,
plus m.
not quite, plus 1.1 m.
Yeah. Okay. Yeah. So this is our total momentum for the left side.
Yes? And this must equal to that total momentum, which is on the right-hand side. So just the
Yeah.
way I've simplified the momentum at the beginning, can you simplify the momentum after now in a
Yeah.
similar way?
So you can do 1.12 times 0.7 m.
I think you want to say plus rather than times, because remember you're finding the total.
Yeah. Plus. Sorry. Mhm.
So
That,
now, absolutely. So now there you go. You've got now an equation which you can do with maths now. It's an equation that you can solve using the skills that you've got for solving algebraic equations.
okay, okay, so maybe that should be easier if we do it the other way.
Okay.
Uh, wait, sorry.
Okay, so let's see what you've got.
Sorry,
Down to the
6.
bottom of your page, sorry, Jay.
Oh, sorry.
No problem. Okay, there we go. And what you get as your final answer?
My M mass equals to 6. So,
It can't be 6. Just check that again.
okay.
0.24 divided by 0.4.
Oh, no, sorry, 0.6.
0.6. And we're going to need units as well.
So 0.6 kg equals to M.
Correct. Okay. So that was a nice little question, which really made you follow this conservation law strictly and looking at
Yeah,
each mass and its velocity, adding that to another mass and its velocity, that product, and so on and so forth.
yeah,
Okay, great stuff. Now, the next thing we're going to have a look at, so far we've looked at sort of collisions. We're also going to have a look at explosions as well. Okay.
okay,
Now, just to
okay.
start us off, if you had number 3, how would you go about doing number 3? Now, this is not too different to one that you just did at the start, one of the questions. So, have we got number 3? So this is two things moving apart in different directions.
Yeah, yeah.
Remember the key thing that we said, it's like those skaters. What do you have to realize about the momentum of two
Yes.
things that are moving apart?
Could you draw a diagram to show it?
Yeah,
So we know the cannon is actually 600 kg,
yeah,
and then that's recoils at speed 0.5 meters per second. So we know it's moving this way,
yeah.
0.5 meters per second,
Hmm.
and then the ball is being fired. This ball is being fired at 0.5 meters, and it's 12 kg,
Yeah,
and it's being fired at what is it, 0.5 meters per second.
not quite.
No, sorry. You want to calculate that velocity. So
Correct.
yeah. So if we do 0.5, if we try and work out the momentum,
Yeah,
so 0.5 times 600
yeah,
gives us 300.
good.
And then we know 300 kg meters per second is equal to 12 kg times our velocity.
Well done.
And then 300 divided by 12
Good.
is going to equal to 300 divided by 12. 25 meters per second.
Good. Well done. Okay. Part B.
On the sheet.
No problem.
Okay. B suggests how the recoil velocity would have been different if a 4 kg animal was using to. Would that be? Okay, would the recoil velocity be much less?
Absolutely correct. Spot on. It would be much less. You're absolutely
The
right.
momentum have to equal each other, so that means the
Yeah.
momentum is going to be less. So.
Yeah, that requires speed to be much less. Good stuff. Okay. Well, Jay, we're gonna have a quick recess, quick little break, and
Okay.
we'll resume and have a go at a few more questions and other aspects of this momentum topic. All right. So
Yes. Okay.
it's now 14:41. So if we meet up at about 14:46.
Yeah. Okay.
Yep.
46. That's fine.
Yeah.
Yeah.
I'll see you shortly. Nice and Jay. All right. See
See.
you.
Yes. Okay. I think you're still on mute, Samuel.
Sorry, Jay. Yeah, now you
Uh,
can hear me.
yeah, I
Yeah.
just checked the score as well. Yeah, I saw it's 32.
Oh, is it? I didn't even actually see that. I was
Yeah,
covering my screen. Oh, 3-2. Okay. There we go. Yes, 3-2. All right. So they eventually won. Oh, definitely. They'll be happy after that loss to
yeah.
Crystal Palace, isn't it?
I think we got Arsenal on Monday, haven't we?
Yeah,
Monday.
yeah, yeah. Not until Monday, I know.
Yeah.
Um, so it'll be a quiet one. It'll be a quiet weekend, which is not a bad thing.
Yeah, exactly.
Right. So the next thing now,
All right.
now that we've looked at explosions and understanding that it's all about really them being in sort of moving in with opposite values, the sort of values, opposite signs, but same momentum. Yeah. If you've
Yeah.
got an explosion, that's the key thing to remember there. Now, the next thing we're going to look at is this thing called impulse.
Yeah, that's good.
You know, it is related to momentum as well.
Yeah.
So so we started off firstly with our formula, which says that resultant force is, can you remember that formula?
Resultant force equals mass times acceleration.
Correct. Okay, so it's a very important one, and you will not be given it in the formula booklet, so you'll be expected to remember it. So now can you remember the formula for acceleration? Can you remember the formula for acceleration?
Is acceleration equals to, is it something like change of velocity?
Yeah, yeah. So V minus U over T. What do you think
Okay.
the V and the U stand for?
So the V equals to the final velocity and U equals to
Correct.
initial velocity.
Correct. Final velocity, and this is the initial velocity.
Yeah.
And this here is just the time.
Yeah, yeah.
It has to be in seconds, and again, meters per second, meters per second. Okay?
Yeah.
Now, if I take this formula for acceleration and I put it into this equation,
Yeah.
yes, which looks at resultant force, then
Will
I end up with an equation that looks now
it be
resultant
R?
force. Oops, my phone's ringing just a moment. Sorry, Jay.
No, no.
Yeah. So I'm still in the lesson. Do you want to text me thing, please? Okay, so the resultant force we get is mass on the outside, which is given the symbol m, and acceleration is v minus u over t.
Yeah, yeah.
Okay, so now I get, if I expand this, because it's in brackets,
Yeah, yeah.
I now get mv minus mu, everything over t. And this gives
Wouldn't
me,
it be MT as well?
sorry,
Wouldn't it be MT as well because you're expanding it so
not
times v?
quite, that's the same as m over 1. And if you
Oh,
multiply two fractions, the top multiply together and the
the
bottom
bottom.
multiply together.
It's just 1 times T, so yeah.
Yeah,
Okay.
correct. Absolutely. Good question. Worth double checking that. Now, when you look closely at what we have here,
Yeah.
mass times initial velocity. Where have we seen that, this mass times velocity business?
Is it in momentum? The
Correct.
momentum.
So this
Oh,
here is what you call the initial momentum. This is the initial velocity.
okay, okay.
And this here is the final
The
momentum.
final.
Correct.
Okay.
And this here is time as per usual in seconds. And this here is
Yeah.
a force, which will be in newtons. Yeah, all forces are measured in newtons. Now, what do I see? I can rearrange this. So times by t on both sides, times by time, and the two
Yeah.
cancel off, isn't it?
Yeah, yeah.
Okay, so over here, I now have a unit that's got newtons multiplied by
By
second.
second.
And that is why the quantity or
Um,
momentum is also the Newton second, because it's an
ah,
equation. So the left-hand side, the units on the left-hand side have to be equivalent to the units on the right-hand side.
okay, yeah,
Okay, so far so good. So what
yeah,
this is telling us actually is that if something changes its momentum over a long period of time, then the force that acts is far less. So
yeah,
let's imagine, let's just give an example of a cricket ball. Yeah. And let's imagine that that cricket ball is, let's imagine it's got an initial velocity of, what's a sensible bowling or speed that a cricket ball will leave a bat?
um,
Just a sensible speed that you reckon.
well, it'd be fast, so uh, probably about 100 miles, meters per second, I don't know.
100 meters, oh, I think that's a really, that would be very, very fast. But it's
Would
going to
it?
be pretty high. So maybe about 20 meters per second.
Oh, okay,
Yeah,
yeah,
even that's extremely fast. But let's imagine that's its initial velocity, 20 meters per second, and I'm going to catch it. So what would
yeah,
its final velocity be when I catch it, when it
would it be
stops?
zero?
Zero,
Because it's,
right.
yeah,
Now I've got an option. I can either make it go from 20 to 0 in a
yeah,
space of 20 seconds, or I can make it go from 20 to 0 in a time of 1 second. Which of these will be the better way to stop it? To stop it in 1 second or to stop it in 20 seconds?
wait, sorry, say that again, so,
So a cricket ball that is initially traveling at 20 meters per second,
yeah, yeah,
I'm eventually going to stop it and catch it because I'm fielding, right? So I'm going to bring it down to 0 meters per second. Now I've
okay,
got an option to take it from 20 to 0 in 20 seconds or to take it from 20 to 0 in 1 second. What is the
oh,
better option for me? The
well,
catch.
would it be in 20 seconds because it's going to hurt less because it's going to slow down?
Absolutely, it's going to hurt less. You're absolutely right. And that's why when you see them catching, what do? They
They
bring it
bring it
down.
up,
They don't
yeah,
just catch it.
yeah, because it's going to
Yeah,
hit the hands. They try and create the same momentum so it comes down.
you're right. So if I look at the force using this formula,
Yeah,
let's imagine it's about uh, 0.3 kilograms. Yes, the
yeah,
mass of the cricket ball. So it's going to be 0.3. Its final velocity is 0 minus 0.3. Its initial velocity is 20. And if I catch it in 20 seconds, the resultant force or the impact force I will feel will be, well, that's just 0 minus 3 times 20 divided by 20. So I will feel an impact force of minus 0.3 newtons. The reason why it's minus is because that's the force from my hand onto the cricket ball.
wait, sorry, so I don't get that bit. So you cancelled the 20 off with the, oh,
Well, this is
oh,
0. So this is
yeah,
0.3 times 20
yeah,
divided by 20. So the two 20s cancel off. So
yeah,
that's
but then isn't
0,
it
isn't it?
just 0.3 minus 0.3?
Yeah, that's the answer. Minus 0.3.
Oh,
Yeah, no
okay,
problem. But if I try and do the same thing and I do it in 1 second, well, I'm going to write it out the same way, only that this time my t is 1. So I'm going to
yeah,
divide by 1 second. Now you see that the force I feel is a minus 6 Newton force. That's the force I feel on my hand. Whereas if I slow it down in 20 seconds,
yeah,
yes, I only feel a force of minus 0.3 Newton. This hurts far less than that.
okay,
Okay?
yeah,
And for the same reason again, if somebody's jumping from a tall building, about to hit the ground, they don't land with their feet straight. They bend their feet.
uh-huh,
Now, why do they bend their feet? It's to slow down the time over which they're going from that high velocity to 0.
yeah,
So that the impact force is reduced when they
uh-huh,
land on the ground.
yeah,
Okay?
yeah,
That makes
yeah,
sense?
Yeah, yeah,
Okay, good. So we know then that Ft, F times T is equal to mv minus mu. I've just rearranged this equation. Okay, that's force times time. Okay.
yeah.
This quantity here, Ft, is known as the impulse.
Okay.
That's what we mean by impulse. So it is a measure of the change in momentum.
Yeah, yeah,
Now, from here as well, we have what is known as Newton's second law. This here, this expression is also known as Newton's second law. And what it says is that the rate at which momentum changes, because you're saying
yeah.
final minus initial, so you're looking at a change, and
Uh-huh.
it's a rate because you're dividing by time. So the rate
Yeah.
at which momentum changes is directly proportional to the resultant force.
Okay.
Okay, that's what Newton's second law states.
Yeah,
The
yeah.
rate at which momentum changes is directly proportional to the resultant force.
Okay. Hmm.
Okay, so far so good.
Yeah, yeah.
Okay, brilliant. So what we're going to try and do is let's try and see if we can pick up a few questions. Now, for the same reason, it's the reason why you have crumple zones, yes, in cars.
Yeah.
Why do they have crumple zones? Because they want the speed of a car in an accident to go from whatever speed it's going at to zero in a long time.
Yeah, so it's less impact, but
So there's less impact force on the passengers. If they didn't
yeah.
have that, there would be a high force. Okay?
Yeah.
All right. So when I've got these, if I just take this off, actually, I've got a set of questions I want to use from, but they're on my USB now. Where's my one second, Jeremy. All right, just gonna have to get some from here, and okay, just gonna have a few. I got a few of these momentum. Oh, can you see my screen, Jay?
Yes, yeah, yeah.
All right, great.
Okay, so
The first question.
which is a great definition. Is it
Take your time.
um is it C?
Is it C? Okay, well done. It is C, yeah? So P
Yeah.
over M, kilogram meters per second. Well done. Okay, next one. Let me try and use this. Yep.
Okay, so which statement correctly describes the law of conservation of momentum? Is it C?
The momentum before is more than the momentum after, not quite.
Oh no, no, sorry, I said momentum.
Remember the law of conservation of momentum. If you remember what I said about it, that the momentum before an event or collision is always equal to the momentum
Oh,
after an event. That
oh
is why,
yeah,
remember when we were doing our calculations, we were finding the total momentum before and
yeah,
then making that equal to the momentum after as well. Okay,
yeah. I remember. For some reason, I don't
no
know why,
problem.
but
You get it?
yeah.
Okay.
Okay. So impulse is equal to. Is it b even though it's a change in velocity? No. It's not b. So it's divided by time. Is it? Sorry, c.
Correct. Well done. Good. It is C. Excellent. And move on to that one now.
Okay. So,
I might have to shrink this a little bit. Sorry.
okay. Don't know. Thanks. Is it? Don't know. Hang on. Can you scroll down a bit more just so I can see the bottom
Yeah.
bit?
Yeah. You're absolutely right.
Oh, yeah, thanks.
Yeah.
Is it D?
The time of position is elongated for the passenger. Yeah. Correct. Okay. Next one. 5.
Would it be B?
This is much well done. So did you use algebra for that one, or did you put some numbers?
I just put 2 and 2 into each one, then just worked it
Oh,
out.
played around with it. That's fine. Okay.
Is it C?
Yeah, correct. Yeah, gotta have the opposite signs because they're moving in different directions, aren't they? Good. You
Yeah.
didn't get caught out with that one. Excellent. All right, now we already saw that one. All right, what about this one?
Okay, fine. Would it be A?
Lengthen time of, you're absolutely right. And using our formula, therefore, a lesser force. Good.
Yeah. Is that because, do you know, going back to it, is that because the padding is gonna like extend the time that
Yeah,
they're
over which they come to a stop.
yes, yes.
Correct.
Okay.
Then they experience less of a force. You're absolutely right. Okay.
Okay.
Number three.
Is it B?
Is it B correct? Spot on. Good.
Also, do you know why does the airbag deflate when it's hit by the driver's head?
Yes, the reason, okay, it's all to do with the fact that then again, if it doesn't deflate, if it's already inflated, then there'll be a greater impact on the face.
Oh, and
The face
it's
will
just like impacts
come
the
to a stop. Yeah. So whereas it, as it's because it's deflating, it means it almost lets the person keep moving forward until they finally
yeah.
come down to zero at a much less
Uh,
or in a much longer time. So the
oh,
rate
okay.
of momentum um, is reduced. Okay.
Yeah.
Good question.
Is it C?
Very good. The total momentum of the system is zero because before the shot is fired, both
Yeah.
the gun and the bullet are at 0 meters per second.
Yes. Yeah.
So the total momentum is zero. And after as well, when it's fired, the total momentum will still be zero as well
Yeah.
because
They
they've got
cancel.
momentum in opposite directions. Yes, so they cancel out and you get zero.
Yeah.
Good, well done. Okay, we'll move on to the hard ones now. All right. So you will need a calculator for this
Okay.
and your pen.
Would it be C?
Okay, C. Okay, calculate momentum of the toy train before the collision. Yeah. So, oh, just check that one.
Okay. Because wouldn't you convert 75 grams to kilograms?
Okay, yes. Is that all you did?
Yes, to 0.075
Good. And then you multiplied it.
by 0.5 and then got 0. Oh no, no, sorry.
Yeah.
Oh no, it says B, sorry. B.
Okay, I mean B, yes, correct. Absolutely.
Okay,
B
I
is,
didn't see my zero in front of the three.
yeah, I know they've kind of changed the significant figures there. Okay.
Yeah.
Can you remember the formula for impulse?
And that's the only formula I didn't write down. I wrote all the acceleration one.
No worries. So impulse one, I'll bring
Isn't it just the acceleration formula in the relative force, the resultant force one?
not quite. I'll just bring this.
Okay.
So this whole thing here, this
Yeah.
product times T is what we call the impulse. An
Yeah.
impulse is the same as the change in momentum.
Yeah. 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 Okay.
That's initial momentum, that's final momentum.
Yeah.
Okay?
Yeah. So, yeah.
Okay, good.
Okay. I'm just gonna grab another pen because my pen's
Okay,
running.
go for it.
Yeah. Is it 750 newtons second?
Correct, well done. This one is a tough one, so take your time with this one.
Okay.
Any luck with that one, Jay?
Is there? I was just gonna ask, is there a formula for pressure? Like,
Yes, pressure is force divided by area.
okay, oh yeah, that high pressure
Okay,
equals to force divided by area. Okay,
correct.
nice. Okay. Is it C?
See, okay, so nearly there, so nearly there. We're just gonna look at what he did there. Oops, gonna take some of this off.
Do you want to put the visualizer on as well so you can see my working
Yeah,
out?
absolutely. Let's have a look at your working and see what you did, and then we can correct it just to see where you may have gone wrong.
I think it's the sun.
Yeah,
Let me just
so that's it. Yeah, it's
quickly shut the blinds so you can see a bit
yeah,
more.
it's quite bright. Yeah, please, thank you. So, where did you start off from?
So I did, um, so I,
So, okay,
um,
pressure is force divided by area. Good. So, what did you need to find first? You needed to find, okay, that's the change 500 times 6.5. Good. 3250. So, you know, FT is 3,250. Good. Okay.
yeah.
Now, where you got caught out, you said 250 times 50. Now, the pressure should always be in pascals. Now, that is in kilopascals.
Oh, so it'd be
Area.
0.2.
Yeah, and the area should always be in meters square.
Oh, okay, okay. I was thinking, yeah, something was going to go wrong there because I didn't know what the units were supposed to
Yeah,
be.
not to worry. So kilo, you'd want to change that to 250,000.
Okay. Yeah,
Not quite. So remember, kilo means you times whatever it is, that number by 1,000.
yeah, oh yeah, sorry, yeah, yeah. So
Not to worry.
250, the other way, yeah, it's 250,000
Yes,
Pascal.
good.
And then that's times by, and then you say meters squared.
Yes, so change 50
Yeah.
centimeters square to meter square.
Is it going to be 0.005?
Um, 0.005. So what was your conversion factor?
Isn't isn't 1 meter squared 1 meter squared equal to 100? No, isn't it equal to 10,000 centimeters squared?
Yes, well done. So you've got to divide that by 10,000, haven't you?
Yes, yeah, yeah.
Correct.
50. 5 times 10 to the minus 3, so 0.005.
Yeah, 0.0005, correct.
Yeah.
Okay.
Then, yeah, that's right. And then 250,000. That's 1,000. 250. But I still get 1,250.
But you had 12,500 before.
Oh, yeah. Oh, yeah. Yeah.
Yeah. Okay.
And then,
So that is your force.
yeah. Yeah. And then if you do 3,250
Yeah.
divided by 1,250.
Yeah.
Oh, I did it there, but I thought when I was doing it the first time, I forgot to put my other zero here.
Okay. Okay.
I made that mistake here. 2.6, sorry.
All right.
So 2.6 seconds.
Correct. So the car will come to a stop in 2.6 seconds. Okay, good. Well done. Four.
Okay, so a gas monitor strikes. Mm.
So can you remember the formula for kinetic energy, Jay?
Not really, no.
Okay.
No.
So it's half mv squared.
Oh yeah, half.
Half times the mass, which should always be in kilograms, and the velocity, which should always be in meters square.
Yeah.
Sorry, meters per second, not
Oh
meters per
yeah.
second. Sorry.
Yeah. Okay. So, um, um, but we don't know what the mass is of the gas molecule. So,
It doesn't matter. You can even put
okay.
a number if you want. The mass is not going to change, stays the same.
Oh, I get what you
If you
mean.
want.
Yeah. Okay, so could I know it's not going to be correct, but could we just say the molecule's 1 kg?
Yeah,
Even though
that's
it's not.
fine.
Yeah.
Yeah.
1 kg times our velocity, which is what's up? 200. So 200 squared is. And then,
Okay, good. You know the units. Well done. Okay.
yeah,
Yeah. So that's the kinetic energy before it hits the wall. And that is the same value when it leaves.
yeah. Yeah, right again, sorry. So is it C?
Now
No,
take
minus GD, sorry.
E. Correct. Going in the opposite direction. So they're trying to check, do you know that velocity is a vector? Okay. Another really
Mm.
question to assess that. So it does move off with minus 200 as opposed to 200. Okay. Because 200 is for the right. Well done. Well done. Okay. And lastly, question 5.
Okay.
Good. Good.
Would it be A?
Correct. Well done. Okay.
Yeah.
Nicely done. And that was the last of the hard ones, and you've done really, really well because this particular topic sometimes can take people a while before they get their head round what's going on. Okay, so
Yeah.
you definitely have a good general understanding of what's going on.
Yeah.
Now there's only, hang on, grade 9 question I wanted us to look at. And I bring, well, I'm trying to share my screen. Oops. I'm gonna put that here.
Okay.
I don't know how clear it is. I could try
Um.
and bring it a little bit closer down.
Yeah, that would help. Yeah.
Yeah. Uh,
Okay. Thanks.
this is a grade 9 AQA question. You know about that one, Jay?
Okay. Yeah. So, oh, just 3.2.
3.3. We're just going to go straight
Okay.
to
So, bullet with a mass of 10 grams is 5. Right. Okay.
Good, well done.
Well, I've kind of got the left and right wrong, but does it matter?
No, they look
Really, isn't it?
correct to me. It's being far to the right. That's how I'm seeing it, unless your visualizers.
Oh no, oh sorry, didn't see the rifle recoil. I thought that was the bullet that moves to the left. Yeah, it is right. Sorry, yeah. Okay, so calculate the velocity of the wooden block. So is the wooden block like moving? Gonna move back then as the bullet hits it?
So yeah, the yes, it is going to move when it's
Yeah, I,
going to become like a situation where you have the car hitting the trailer that I had,
yeah, yeah. The trolley stuff as well. Yeah.
the trolley again. It's very similar to that.
Okay, yeah, I know what you mean. Yeah.
Yeah,
So there's like two steps to this question then.
there are two steps, absolutely. Well done.
I've done it the wrong way.
Yeah, just think a little bit here, Jay. What you've now got is, you know, the velocity of the bullet, you know, the mass of the bullet. Now
Yeah.
one collide with a block.
Oh, yeah. Sorry, I don't know why I'm working on that. Yeah.
Okay.
So when it collides, yeah.
So then it's now going to move together. So you're looking at what is the momentum firstly before the collision and the momentum after the collision.
After,
Yeah.
Yes. Yeah.
Okay.
So you're gonna do. So we know the momentum before the collision is 400 meters per second. No, wait, hang on, that doesn't make sense. So.
Okay, so take your time with this one. Can I zoom out? So you've got a number of systems here at play, isn't it? You've got your gun with a bullet. That's the first system.
Yeah.
Then at some stage, it's a big wooden block, if you like. And then now you've also got another system, which is your block and the bullet.
Yeah. Yeah.
Okay. So before they collide, the speed of this is 0.
Yeah.
And this here has a speed of 400 meters per second. It's a mass of 0.01 kilos. If you times those two values to get the momentum plus the momentum of this, that is the momentum before the collision. And that will equal to when they move off together, similar to the question with the moving cars colliding. Do you remember?
Yeah. Yeah.
It's no different from there. It's very much the same thing. Oops. Oh, Jeff, for some reason my board has just disappeared. It's crashed or something.
Yeah.
Not to worry anyway. We have come to the close of this session. What I'll do is I'll try and send you that question so you can have a go at it in your own time as well. Yeah?
Yes. Okay.
When you are slightly not as being overly paced, but this is good what you've done today. Okay, right. Good stuff, Jay. So I'll see you tomorrow then. And
Yeah.
you seem to have caught a little bit of a cold. Are you
Yeah. I had that yesterday when I got back from school. I don't know why. I think I just got a bit of a temper and I just feel a bit tired as well. Yeah.
Right. Okay. See how you feel. If you feel you want to rest tomorrow, we can always push it to some other day in the week.
Yeah, I should be all right. Yeah.
Okay. Cool. Otherwise, if you're feeling good, then we'll carry on as per usual. It
Yeah.
will be in the afternoon.
Yeah.
Any preference? What time you'd like? Afternoon then.
Afternoon.
Late afternoon.
I'm not sure. Whatever time's good for you.
Cool. Okay.
Maybe
I'll send you a message then. But as a provisional, let's go for 2 o'clock.
2 o'clock. All right, that's fine.
Yeah.
Yeah. Okay.
Cool. Nice one, Jay. Have a good one. Yeah. Hope you get better as well.
Cheers. Thanks, session.
Oh, you're welcome. See you soon.
See you.